Multimodal models are capable of processing and generating multiple types of data. For example, models that can convert text prompts into images, transcribe speech, and even caption images. In this video, I'll introduce 3 ways of developing multimodal AI systems by building on top of large language models. I'll start with a high-level overview of each approach, then share Python code demonstrating how to use LLaMA 3.2 vision to solve various image-to-text tasks. And if you're new here, welcome. I'm Shah. I make videos about the things I'm learning about and building in AI. If you enjoyed this content, please consider clicking the subscribe button. That's a great no-cost way you can support me in all the videos that I make. The goal of this video is to give a high-level introduction to multimodal models and describe a specific type of these models which build on top of large language models. Starting from the basic question of what is a multimodal model. Here I'll define them as AI systems that can process multiple data modalities, either as input, output, or both. Some notable examples of multimodal models include GPT-4o, which can take in text, images, and audio and return back text. Another one is Black Forest's Flux model, which takes in user text prompts and generates images based on those prompts. Or even a AI system like Suno AI, which can take in text prompts from users and generate music. Although these are all examples of multimodal models, they are all developed in very different ways. So here I'm going to talk about a specific type of multimodal model which builds on top of large language models. These are sometimes called multimodal large language models or even multimodal language models. I know the naming of these things may not be so great, but that's what they call it in the literature. And so the basic idea here is that we take a large language model, whether it's pre-trained or we take the architecture of a large language model, and we augment it in some way to be able to process multiple data modalities. What that might look like, we have our LLM, we augment it to also be able to take in images and audios, and then add some components to the end of it so that it can also generate images and audio. The key idea here is that these multimodal language models use LLMs as a core reasoning engine. We might ask ourselves, why use language models to go multimodal? Aren't these optimized specifically for text? Well, there are a couple reasons why we might want to do this. One, LLMs have demonstrated a strong ability to acquire world knowledge, meaning that through the model's pre-training, it learns a lot about the world, and it also learns a lot about concepts which we might not initially associate with text. There was a popular paper, I can pop it up on the screen, called Sparks of AGI, put out by Microsoft, and there they were showing examples of how GPT-4 was able to draw images and understand spatial concepts and do spatial reasoning even though it was strictly trained on text. So it seems that even though large language models are only trained on text, they also learn concepts which may be helpful for processing other types of data. Another thing is that text prompts is a natural way to enable zero-shot capabilities. So the meaning of zero-shot is basically using a model to perform a task that it was never trained on specifically. Text prompts, which are native to large language models, are a natural way to steer a model to perform these novel tasks through basic text descriptions. So here I'm going to talk about 3 general paths to developing these multimodal language models. So the first is going to be augmenting LLMs with basic tools. The second is going to be augmenting LLMs using so-called adapters. And then the third and final approach is to create a unified model which is trained from scratch. So starting with path 1, this consists of adding external modules to do X to text or text to X, where X represents any arbitrary arbitrary data modality. It could be images, audio, EEG data, time series data. It could be anything. So the way this works is that we'll have our large language model, which is only capable of taking text in and spitting text out. And if we wanted to, say, add the ability to process audio or speech, a very simple way of doing this would be to pass any input speech into the system through a speech to text model like Whisper, and then passing that subsequent text into the large language model. To do reasoning, we simply just prompt the large language model to say, do tasks based on the transcript. For example, if you wanted to summarize YouTube videos, you could take the audio, transcribe it with Whisper, and then pass the transcription to the large language model and simply prompt it by saying, please summarize this YouTube video transcript or something like that. We can also do something similar on the back end. So let's say we wanted to generate an image. We can tell the large language model to generate a prompt that will be passed into a image generation model. For example, it could generate a prompt for Flux, and then Flux will generate an image. And indeed, this augmentation of large language models with external tools is how the early versions of ChatGPT was able to process multiple data modalities. And so some pros of this is that this is very simple to implement. You don't have to train any models. You don't have to be a machine learning engineer. You can get by with basic software engineering and connecting some APIs together. The other pro is that no training data is needed. You don't need to train a speech to text model. You don't need to train an image to text model. You don't need to train any adapters, as we'll see in the next slide. You can just use all these pre-trained models out of the box and stitch them together to fit your needs. But of course, there are some cons. One is that this type of system will have limited capabilities. For example, there may not be a pre-trained model that reasonably translate an arbitrary modality into text. For example, if you have sensor data collecting information about the weather, there may not be a natural way to translate that into text and pass it into the large language model. Another limitation here is that you can only customize the model through prompting the large language model. So this may make it challenging to steer the model's performance in a particular direction. Another note about customization is that since these are all independently developed modules, there's no guarantee that they're going to play nice together. So it's going to take a lot of tricks and prompt engineering to get this to work well. So a way we can unlock better customization of this type of multimodal model is by training so-called adapters to glue together different components of the system. So specifically adding encoders and decoders to the LLM, which are aligned via fine-tuning. So to show what this looks like, we still have our LLM, which only takes in text and outputs text. Then let's say if we wanted to add images, we can use a so-called image encoder like Clip, which takes the image and translates it into a dense vector representation. And then what we can do is train a relatively small number of parameters called an adapter to translate the dense vector representation of the image encoder to a representation that is compatible with the LLM's internal concept space. And so this can be done in a few different ways. Popular ways by using image caption pairs. So you can train this adapter such that the image representation is similar to the LLM's representation of the corresponding caption. And then we can do an analogous thing on the output side. Let's say we wanted to generate an image. We can get a image decoder, which translates a dense vector representation into an actual image. This might be a stable diffusion model. And then we'll glue together the vector output of the large language model to the vector input of a stable diffusion model using a decoding adapter. A key thing here is that there isn't a need to retrain the image encoder, image decoder, or large language model in this case. The only things that need to be trained are the adapter weights. So either the encoding adapter or decoding adapter or both. The fire emojis are indicating the trainable parameters while the snowflake emojis are indicating the parameters which are frozen. Some of the pros to this approach is that you get better customization. Through adapters, you have a way of aligning the different pre-trained models so that they work nicely together. Another upside is data efficiency. Since we're only training a
relatively small number of parameters through these adapters, you don't need massive training data sets. You can probably get good performance with on the order of hundreds or thousands of examples. The cons, of course, is that this requires training data, while in the previous approach, we didn't require any training data. So this is a bit more work on the machine learning engineering side. And also this is a bit more technically sophisticated than before. So now you can't really get by with just basic software engineering and API calls. You're going to need to put on your data engineering hat, you're going to need to put on your data scientist hat and your machine learning engineer hat in order to develop a system like this. And I also want to point out a few nuances here. So there are a wide range of models in the literature that follow this approach, and sometimes they'll take it one step further in that not only training the adapters, but after doing so, there'll be a second stage of fine-tuning where they'll do an end-to-end fine-tuning of the system. Another nuance here is that sometimes people will add cross-attention layers inside the large language model, which will allow the model to mix the different modalities together. And another nuance is that, maybe you want to bring your own pre-trained model. So you don't want to use a readily available model like Clip. You want to create your own image encoder on your own custom data set, but then you want to plug that into an existing large language model. So there can be a lot of nuance here than the simple picture I've shared. And so if you want to get a better sense of all the different ways that this approach can look, here are several examples from the open source community. Now it seems LLaMA 3.2 Vision is gaining some traction, and then there are several others as well. The final way that we can make large language models multimodal is by mixing modalities at pre-training. In other words, training the LLM to be multimodal from scratch. This will greatly simplify the inference architecture because the model can natively take in any data modality and spit out whatever data modality you train it to do. So some key pros of this is that you get seamless modality integration. You don't have to worry about external modules and pre-trained models and gluing them together with adapters. It's kind of like how Apple builds their products to be seamlessly integrated end to end, as opposed to like a gaming PC, which hobbyists will source and put together on their own. Another pro of this is faster inference times. Since data doesn't have to be piped and passed through different models and everything is just passing through a single model, there's less computation that needs to be done. So there will be faster inference times. And this is something that was observed with GPT-4o when it first came out. But of course, the cons of this approach is that it comes with many difficult technical challenges. So the models that we've seen that use this approach come from teams of dozens of researchers and engineers at top institutions. So this isn't going to be like a fun weekend project for anyone. Just like training large language models from scratch comes with massive data and compute requirements, training a multimodal large language model from scratch will require even more because of the added modalities. Unless you've got a team and tens of millions of dollars behind your back, it's unlikely that you'll be able to develop a model like this that's comparable to what we're seeing in today's landscape. Some examples of this that I'll call out are presumably GPT-4o and Gemini. Although they don't share all the details of how these models are developed, it seems that they do have some kind of unified pre-training. And then some other ones in the open source community are Emu3, Blip, and Chameleon. So now that we have a basic idea of how these multimodal language models are developed, let's see what they can do. So in this example, I'm going to use LLaMA 3.2 Vision to perform a variety of image-based tasks. So in order to run this example, I'm going to use Ollama, which allows you to run these models locally on your machine, so you don't need to make any API calls. In order to get Ollama installed on your machine, you'll need to go to their website, ollama.com, and then you'll need to download it for your operating system. Another requirement is to install their Python library, so it's a simple pip install Ollama. Jumping into the code, there's only one import, so we'll just import Ollama, and then we'll download the model using this line of code here. So here we're grabbing LLaMA 3.2 Vision, and this will be the 11 billion parameter version. And then we can use this model to do basic visual question answering. So it's actually pretty amazing. In just one import and then one line of code, we're already ready to start using this model. But anyway, we can pass an image and question to the model. model using this syntax here. So we'll do Ollama.chat, and this is very similar to the syntax for OpenAI's API. So you specify the model, and there are several models available on Ollama. So we're going to use the one we just imported, and then we'll define the messages. We'll just have one message, which will be stored in this list of dictionaries. So we specify the role. This message is coming from the user. The content of the message is the text associated with it, which is going to be what is in this image. We can also pass in images. These are saved in a folder in the project directory called images, and it's a photo of me sitting. We can also pass in multiple images. It's not limited to just one. And then with that, we can just print the response of the model. This is what the image looks like. It's a photo of me from a networking event in Fireside Chat. And then I asked Llama 3.2 what is in this image, and this is what it said. It said this image shows a man sitting on a yellow ottoman with his hands clasped together. He is wearing a black polo shirt with a name tag that says Shaw and a black baseball cap with the white text that reads the data entrepreneur. The background of the image appears to be an office or lounge area with a large screen on the wall behind him displaying a presentation slide. There are also several chairs and tables in the background, suggesting that this may be a meeting room or common area for employees to gather and work. So I would say for the most part, it does a pretty good job. My polo is actually more of a gray than a black, but I guess that's pretty close. It spelled entrepreneurs wrong, but it's actually pretty amazing that I was able to read that. I can't really read that from this angle. This is indeed a lounge area behind me in a co-working space. So it does a pretty good job just from this image without any additional context. Another thing we can do is streaming. So on my machine, I have the M1 chip, but it still took like 30 seconds or a minute to generate that previous response. To make that waiting a bit more bearable, we can enable streaming. So this is kind of like when you go to ChatGPT, you type in a prompt and it'll start spitting out text one word at a time. It's just better from a user experience standpoint. So we can easily enable streaming with Ollama using this syntax. So we just have the same Ollama.chat, same exact inputs, but then we just have this stream equals true argument. And then what we can do is print text from the stream in a for loop. And then if we run this, we'll see the response appear one word at a time. I asked a slightly different question the second go around. I asked it, can you write a caption for this image? And it gave a different answer, which is pretty interesting. Slightly different prompts, but quite different responses. I'm not going to read through this, but some notable things is that instead of the data entrepreneur, it said the data enthusiast. So it's interesting how that changed. And then also it kind of caught the fireplace the second time around. It started describing the paint and the design of the background. So I think this is a fun thing to play around with locally on your machine. Passing in images and asking questions about it could be a fun thing to do. Describing objective images is one task, but describing humor and memes requires a different level of, let's say, intelligence. So let's see how well the model can explain memes to me. Basically the same exact code as before, but now we're just going to pass it a different image and a different prompt. So I'm asking it to explain this meme to me. So the meme looks like this. This is from a previous video and a LinkedIn post. So I asked Llama 3.2 to explain the meme to me, and this is what it said. The meme depicts Patrick Star from SpongeBob SquarePants surrounded by various AI tools and symbols. The caption reads, trying to build with AI today. The image humorously illustrates the challenges of using AI in building projects, implying that it can be overwhelming and frustrating. So I think it got the gist of the meme. It recognized Patrick, which is kind of amazing when you think about how this model was trained, using that path 2 of aligning an image encoder with Llama 3.2's internal concept space. And then the final thing is optical character recognition. The code looks exactly the same, but now we're going to prompt it to say, can you transcribe the text from the screenshot in a markdown format? And then we'll pass in a different image. So this is from a LinkedIn post describing 5 AI projects. And so not only do I want it to parse this text and write it out, I want it in the markdown format. So let's see how it does. It says, here's the transcript of the text in a markdown format, and it does a pretty good job. The only thing that's missing here is that this should be a header. So there should be a hashtag or a couple of hashtags in front of it, but everything else, it did a good job. You know, I didn't see any spelling mistakes, and then it got the numbering and the bullet points right. The amazing thing about these emerging multimodal systems is really this zero shot capability. You know, before, if I wanted to do OCR OCR, I needed an OCR specific model, and that model may not do Markdown. But now I have a single model that can not only do Markdown, it could probably do HTML, it could do plain text. You can easily customize these models simply by changing the prompt. No fine tuning or model training required. I barely scratched the surface with these 3 examples, but hopefully this gives you an idea of what these models can do. So this was actually the first video in a larger series on multimodal AI. In the next video of the series, we're going to talk about multimodal embedding models. So we actually already talked about an example of such a model in Clip when talking about path 2 toward creating one of these multimodal language models. And basically the way Clip works is that it'll take in both text and images, and it will represent them in a shared vector space such that the text, for example, a silhouette of a dog, will appear close to an image of a silhouette of a dog. And similarly, the text and image of a silhouette of a cat might look like this. Ollama's logo and the text Ollama might look like this. And then Python programming language would be relatively close to Python's logo. So I'll talk about how we can train these models and what we can use them for in the next video of this series. And if you enjoyed this video and you want to learn more, check out the blog posted in Towards Data Science. And although this is going to be a member-only story, you can access it completely for free using the friend link in the description below. And as always, thank you so much for your time, and thanks for watching.